Imagine our planet not as a secure, isolated harbor, but as a fragile biological system drifting within range of unimaginable astrophysical violence. The cosmos operates on physical laws that simply do not account for human survival. Modern astrophysics and paleoclimatology prove that Earth's delicate biochemical balance is constantly under threat from dynamic and unpredictable cosmic events. In fact, researchers estimate the risk of an existential catastrophe or irreversible civilizational collapse occurring within this century stands between 10 and 25%, factoring in both human-made and cosmic hazards. We are surrounded by monumental forces, and the first of these 5 cosmic threats has already rewritten the history of life on our planet. Near-Earth objects, the asteroids and comets left over from the birth of our solar system 4.6 billion years ago. These rocky and icy remnants act as both the messengers of life and the agents of mass extinction. If a space rock larger than 140 meters crosses within 7.5 million kilometers of Earth's orbit, it is officially classified as a potentially hazardous object, capable of triggering a regional disaster. But an object over 1 kilometer in diameter brings the threat of civilization-ending destruction. When a 10-kilometer asteroid slammed into the Yucatan Peninsula 66 million years ago, the immense kinetic energy instantly transformed into a shockwave and heat, plunging the Earth into a long impact winter. The dust cloud blocked sunlight, halted photosynthesis, and wiped out 75% of all species, including the non-avian dinosaurs. Interestingly, this impact was uniquely devastating because it struck a hydrocarbon and sulfur-rich region. A random strike elsewhere would have carried only a 13% chance of causing such global cooling. Even smaller objects hold devastating power. In 2013, an asteroid merely 20 meters across exploded high above Chelyabinsk, Russia, creating an airburst with the energy of multiple nuclear bombs, shattering glass and injuring thousands. Yet our greatest challenge remains detection. While 95% of civilization-threatening asteroids have been mapped, more than half of the 140-meter objects remain hidden in the dark. The tension is real. In late 2024, an asteroid named 2024 YR4 triggered global alarms when initial calculations gave it a record-breaking 3.1% chance of striking Earth in 2032. It took the combined power of global observatories and the James Webb Space Telescope to refine the orbital data and confirm the asteroid would safely miss us, reducing the impact probability to near zero. Fortunately, humanity is no longer a passive target. NASA's DART mission successfully altered an asteroid's orbit through a kinetic impact, proving that with enough warning we can actively defend our world from incoming rocks. The second cosmic threat originates from the very object that makes life on Earth possible, our Sun. The Sun is not a static heater, but a highly variable star, where intense magnetic field lines constantly twist and snap, releasing monumental amounts of energy into the void. While light-speed solar flares hit our atmosphere in just 8 minutes, the true danger comes from coronal mass ejections, or CMEs. A CME hurls billions of tons of magnetized plasma across space at thousands of kilometers per second. When this colossal plasma cloud collides with Earth's magnetic field, it triggers severe geomagnetic storms that induce massive electrical currents both in the oceans and deep underground. In regions where the bedrock has low conductivity, these currents are forced upward into human-made conductive networks like power grids and communication lines, causing catastrophic system overloads. History has already shown us what a direct hit looks like. In 1859, the infamous Carrington event struck Earth just 17.6 hours after a bright solar flare was observed. The storm pushed auroras to the equator and generated electrical currents so intense that telegraph stations caught fire and operators were shocked through their own equipment. That was a rare, extreme occurrence, but modern society is vastly more vulnerable. In May 2024, a massive sunspot launched back-to-back CMEs that triggered the most extreme geomagnetic storm seen since 1989, plunging the magnetic disturbance index to a critical minimum of -412 nanoteslas. Extreme value. Theory models suggest that a storm maintaining that level of intensity could occur roughly every 41 years. If a Carrington-level event were to happen today, the consequences could manifest as an internet apocalypse. While terrestrial fiber optic cables and data centers are somewhat insulated, the undersea cables connecting our continents are critically exposed. These cables rely on long copper wires to power their signal repeaters every 50 to 150 kilometers. A massive geomagnetic storm would accumulate immense currents along these conductive lines, frying the repeaters and plunging continents into permanent digital isolation. High-latitude regions like the east coast of the United States are particularly at risk, whereas areas closer to the equator possess slightly more resilience. To defend against this, we rely on cosmic early warning systems like the DSCOVR satellite, parked 1.5 million kilometers away at the L1 Lagrange point. By analyzing the solar wind in real time, these satellites give Earth a razor-thin 15 to 60-minute window to shut down vulnerable power grids and put satellites into safe mode before the plasma wave strikes. The third threat forces us to look far beyond our solar system, toward the most violent and luminous electromagnetic explosions since the Big Bang, gamma-ray bursts, or GRBs. A single GRB can unleash more energy in just a few seconds than our Sun will emit over its entire 10 billion-year lifespan. Long-duration bursts occur when massive stars collapse into black holes, while short-duration bursts are triggered when neutron stars collide. What makes a GRB so exceptionally lethal is its delivery mechanism. Rather than scattering energy equally in all directions, the radiation is fired into space as highly focused, relativistic jets traveling at near the speed of light. If a GRB within our galaxy were to point its narrow beam directly at Earth, it would initiate a planetary sterilization process. The immediate danger of a GRB is not the initial wave of heat, but the photochemical devastation it leaves behind in our atmosphere. As high-energy gamma and X-ray photons strike the Earth, they trigger an immense ionization storm in the stratosphere. These photons shatter diatomic nitrogen molecules, which then bond with oxygen to form massive quantities of nitrogen oxides. This rapid chemical reaction would systematically dismantle up to 91% of Earth's protective ozone layer on a global scale. Without the ozone shield, lethal levels of ultraviolet radiation from the Sun would flood the surface, fracturing the DNA of exposed organisms, halting photosynthesis in the oceans, and collapsing the entire food chain. Furthermore, the thick layer of brown nitrogen dioxide gas would block incoming sunlight, plunging the planet into a sudden and severe ice age. This is not purely theoretical. Approximately 440 million years ago, the late Ordovician mass extinction wiped out 80% of all marine species, and strong atmospheric models suggest a nearby GRB was the driving force. The devastating power of these bursts was demonstrated recently in October 2022 when the brightest GRB ever recorded, dubbed the Boat, struck Earth from 2 billion light-years away. It was so powerful that it significantly ionized Earth's upper ionosphere and altered our planet's electric field. Interestingly, these cosmic sniper shots might also be the answer to the Fermi paradox. In the universe's first 5 billion years, galaxies were small and compact, meaning frequent GRBs routinely sterilized any planets developing life. Complex life on Earth might only exist today because our solar system is orbiting in a relatively calm, less crowded epoch of the galaxy's history. While gamma-ray bursts are the most energetic, our fourth threat, near supernovae, is far more common and leaves deep scars on planetary biospheres. When a massive star dies in a core collapse supernova, it ejects immense energy, mostly as ghostly neutrinos. However, the shockwaves also accelerate cosmic rays to near light speed, creating a threat that can reach Earth decades or even centuries after the explosion's light first arrives. These high-energy cosmic rays shatter the solar wind's protective shield and plunge deep into Earth's atmosphere, generating devastating muon particle showers. Unlike ultraviolet light, muons can penetrate deep underground and into the oceans, potentially destroying marine life that assumed it was safely out of reach. Geologists have confirmed that Earth was washed in supernova radiation within the last 10 million years, discovering rare isotopes like iron-60 and plutonium-244 in deep-sea crusts and lunar soil. To protect us, an underground network called SNEWS 2.0 stands ready to detect the initial wave of neutrinos, providing a crucial 10-second warning before the destructive light of the next galactic supernova reaches our planet. Our fifth and final threat involves the invisible wanderers of the cosmos, rogue stars and rogue black holes. Ejected from their home star systems or galaxies by immense gravitational kicks. During collisions or supernova explosions, these solitary titans drift aimlessly through the interstellar void. Because a rogue black hole emits no light, it acts as a silent apex predator, detectable only when its massive gravity bends the light of background stars. If a rogue star or black hole were to pass within 100 astronomical units of our Sun, the gravitational chaos would disrupt the perfect clockwork of our solar system. Extensive simulations reveal that Mercury is the most vulnerable planet. A rogue passing could warp its orbit, causing it to plunge into the Sun or collide with Venus, setting off a chain reaction of planetary destruction. In the most extreme scenarios, Earth's fate is chilling. A rogue encounter could use gravitational slingshot mechanics to tear Earth away from the Sun, banishing our planet to the freezing darkness of the Oort cloud. Alternatively, the passing rogue star could capture Earth entirely, stealing us into a new, volatile orbit. Divorced from the Sun's warmth, the surface oceans would freeze solid, transforming our home into a dead, wandering ice world within 1 million years. Fortunately, the probability of such an encounter in the next billion years is exceptionally low. These 5 cosmic threats remind us that Earth is not an isolated sanctuary, yet through vigilant observation, planetary defense, and an ever-expanding understanding of the universe's mechanics, human intellect remains our ultimate shield against the dark.